We're asked to use the cross product to find the obtuse angle between vectors u and v. So there's vector u, there's vector v. And what the cross product does is it gives you a new vector that is perpendicular to the old vectors. Okay, so cross product can help you find something that's going 90 degrees and 90 degrees and crosses with the plane that's formed by these two vectors, u and v. So you can think of a plane in three-dimensional space. The cross product gives you a vector that's going 90 degrees with that two-dimensional plane in three-dimensional space. So it helps us find something that's going in kind of like an opposite direction. Well, opposite's not the right word, because opposite would be, if you have a positive slope, opposite would be negative slope. So perpendicular is probably the right word to use there. Anyway, to find the cross product, I've used the definition the textbook has. In a few other videos, I talked about using the determinant. Those are the same things. Okay, this is the result if you use the determinant of the 3x3 matrix. So, taking a different approach here. Feel free to check out those videos too if you prefer to, if you've used matrices before. And you want to find the cross product. This is how you'd set it up. The coefficients of the first vector here, coefficients of the second vector, j, and then this would be 0, and you would be finding the determinant of this 3x3 matrix. You'll get the same thing up here. U2 just means that we're plugging 7 in here, and that's being multiplied to V3, which is negative 3. U3 means the third coefficient of the vector, u, and then v2. Oops, sorry. Here, this is 0 here for v3, right? This is v1 is 1, v2 is negative 3, so v3 would be 0. What I wrote down here. U3, that's the third coefficient of the third component. And V2 is negative 3. U1 is negative 1. V3 is 0. U3 is 1. And V1 is 1. U1 is negative 1. And V2 is negative 3. U2 is 7. And V1 is 1. Okay, and then when you simplify each of those, 7 times 0 is 0, and then 1 times negative 3 makes negative 3, so a negative 3 makes a positive 3 for the ith component. And then this is 0 minus 1, so we're subtracting a negative 1. I'm going to change that to plus 1j. And then negative 1 times negative 3 makes 3. 3 minus 7 makes negative 4, so that's minus 4k. And if you are used to seeing finding the cross product through determinants, remember for the ith component you'd be finding the determinant of this smaller matrix, so 7 times 0 makes 0, and then negative 3 times, we would subtract that by negative 3 times 1, that makes negative 3. We're getting the same thing, right? Make a determinant of these, so negative 1 times 0 is 0, minus 1, so that makes negative 1j, which we're getting the same thing. And then the last one, that's, I shouldn't scratch that out, but that's a determinant, determinant of these numbers, negative, this matrix here. Negative 1 times negative 3 makes 3. And we subtract that by 1 times 7. Okay, two different ways of doing the same thing. We get the same vector if you were to simplify here. Okay, so that vector is orthogonal to the plane that's made by vectors u and vectors v. So what we need is the angle between vectors, use the crossword, find the obtuse angle between the vectors u and v. Let's see, we got the cross product. We know that that's going to be 90 degrees. 1 second here. So I went and dug up theorem 2.7 for you down here. This is going to help us find the angle between these two vectors that we're talking about, two vectors u and v. We need to start finding the magnitude of the cross product. So we're finding the magnitude of this vector. So that means the magnitude of u, of the cross product of u and v, that's going to be the square root of each component, the sum of each component being squared. And then we also need the magnitude of vector u, which is, vector u is up here. So we got -1 squared plus 7 squared plus 1 squared, and then the magnitude of vector v. And then we'll be able to solve for the angle. So v, we got the square root of 1 squared plus -3 squared plus 0 squared. Okay, so 9 plus 1 makes 10, 10 plus 16 makes 26. 9, 10, 26, yeah. 1 plus 40, so this is 49 plus 1 makes 50, 50 plus 1 makes 51. And then this is 1 plus 9 makes 10, so that's the square root of 10 here. And now it's just plugging it into the formula. Solving for theta. And so we got sine theta. So this is square root of 510. So we can divide that from both sides. Run out of room over there. This is the square root of 26 over the square root of 510. Because we can divide the square root of 510 from both sides. And that's not going to come out to a special trig angles, so we can just use our calculator to finish simplifying here. To finish simplifying, we need arc sine, or in other words, sometimes it's symbolized like this. Because that gets theta by itself. So just clear that up. So we were here trying to get theta by itself, so I used arc sine to both sides because that's the inverse of sine. And then once we evaluate this with a calculator, we're going to have the angle between the two vectors. So here's 510. There's the square root of 510. Copy that to my clipboard, and I'm going to do the square root of 26 divided by the square root of 510. And now, did they say radians? Express your answer in degrees. Book does keep going back from radians to degrees. So my calculator right now is in radians. We're going to switch it to degrees. And then this is the square root of 26 divided by the square root of 510. So now all I have to do is go to trig, second, and there's arc sine. So it looks to be 13 degrees now. 13 degrees, 13.04. I think it says nearest degree. Does it? Nearest integer. So 13 degrees, that would be an acute angle between those two vectors. So you got vector u. Here, let me clear the board. I'll draw this in space. So we have 13 degrees between them. So I just drew two vectors in two-dimensional space to make it a little easier to visualize. But if we had an angle of 13 degrees between the two vectors, the vectors can be drawn, it depends on where their origin is, but the vectors can go infinitely in that direction, right? We can keep going this way, which means we can also go infinitely this way. So if you're asked to find the obtuse angle between the vectors, if this is 13 degrees, then the angle between them, we also have an angle here. This is also 13 degrees. And then there's another angle here that would make a fully straight line. So that's 167 degrees. Okay, this is the angle we found through our calculations, but the angle of 167 degrees is also an angle between those two vectors. That's the obtuse angle. Let's see, I forgot what we had when we did arc sine. But you can also go back to the drawing board with sine too, right? We had a positive. We had a positive ratio of the opposite over the hypotenuse. We had 0.22. When you do sine, an angle of sine, it's positive here, but then you can also get the same ratio in the second quadrant. Okay, so that's also where this is coming from. If you were to solve for this angle here, that'd be 13 degrees for a reference angle that we found in the first place. So from the initial side to terminal side, that's 167 degrees.